Okay, let's begin then. So, if you remember, we have been discussing strain and deformation, and so far we had covered strain in 1 and 2 dimension. So, in today's lecture, we are going to look at strain in 3 dimension, and as a consequence, we have to define what is strain ellipsoid. Like we have talked about strain ellipses in case of 2D deformation. Here we have to define strain ellipsoid, its shape, its orientation. We are going to introduce to you a new concept which we call as preparation of Flynn diagram. And Flynn diagram would essentially would be used to discriminate between constrictional plane strain and flattening type of strain. We will see what do I mean by constriction and flattening. You already know what plane strain is. We talked about plane strain before. Plane strain is nothing but a type of strain which is essentially restricted in one particular dimension, one particular plane. So we know about plane strain. We defined that, and we know there are two types of plane strain. We talked about pure shear and simple shear. So we will see what constriction one and what flattening is all about. Then we are going to introduce another concept, that is what we call as progressive deformation, and we will end this particular topic with the discussion on vorticity. I hope I am audible and all the slides are visible to you. Can someone confirm? Hello, can you hear me properly and see the slides?
Yes, sir.
Okay, excellent.
Yes, sir.
Right. So let's begin with strain in 3 dimension. So strain in 3 dimension is very much analogous to the strain in 2 dimension. Okay, that is what we had already studied. So homogeneous deformation without volume change in 3 dimensions can be considered as the change in shape of an imaginary material sphere. Okay, so we are still discussing about homogeneous deformation, and we are not considering any change in volume. So the volume remain constant just for the sake of simplicity and the sake of understanding. We are considering such ideal situation. Okay, so what we are considering that there is perhaps a sphere, and that sphere would change its shape during the deformation. Okay, so the sphere would become an ellipsoid whose shape and orientation would describe the strain. Okay, so the equation describing this ellipsoid can be written as follows: x square by 1 plus epsilon 1 whole square, y square by 1 plus epsilon 2 whole square, z square by 1 plus epsilon 3 whole square is equals to 1, where of course epsilon 1, epsilon 2 and epsilon 3, it defines the strain in x, y and z directions, right? And we have defined epsilon, what it is, if you remember before in the previous lecture. So the three axes of the strain ellipsoid are maximum, which is denoted as x, intermediate, which is denoted as y, and minimum, which is denoted as z. This is what we call as the principal strain axis. They are mutually perpendicular to each other, where x is equals to 1 plus epsilon, which is nothing but root over lambda 1. Y is equals to 1 plus epsilon 2, which is nothing but root over lambda 2. And z is equals to 1 plus epsilon 3, which is nothing but root over lambda 3. Okay? So if we look at that pictorially, this is a sphere which is before deformation, where x equals to y equals to z equals to 1. That means it's like an unit diameter or unit radius sphere, of course, right? unit radius sphere, and that is subjected to homogeneous deformation, and that uh, particular sphere turns into an ellipsoid after the deformation, and then the the strain along x-axis becomes epsilon 1, the strain along y-axis is epsilon 2, and the strain along z-axis is epsilon 3. And then the mutually, these three axes, of course, the major, intermediate, um, and the small axis can be defined as I said, root over lambda 1, root over lambda 2, and root over lambda 3. Now, you can observe that x-axis is the one which gets stretched maximum, right? It is stretched maximum. And another thing, this particular strain ellipsoid is also called principal strain ellipsoid, okay? So, this particular axis gets maximum stretched. So, this is called stretching axis. The z is the shortening axis because that particular axis gets most shortened, and y, which is in between x and z, and has like a dimension in between x and z, um, and it is mutually perpendicular to z and x. This is what we call as the intermediate axis. Okay. Now, if we consider, instead of a uh, sphere, if we consider a particular cube, what would happen to that particular cube? We are now considering different type of deformation. Okay, so this is an unit cube, x is equals to y equals to z equals to 1, and this is subjected to some sort of strain, and we are observing different types of outcomes, okay, due to different type of stress conditions. Okay. So the first one is uniaxial compression. So that is from one side there is compression only. So where x is equals to y is equals to 1, z is less than 1. So what does that mean? That the dimension along x direction and y direction remain unchanged. Only the z direction gets shortened. Okay. So x equals to y equals to 1. So they remain unchanged and z becomes only shortened. The second type of one, so this type of strain, 3D strain, is called uniaxial compression. Now there is something which is exactly opposite. That is what we call as uniaxial extension. Okay. So what we are doing here? We are essentially extending it along the x direction. Okay. And y and z direction remain unchanged. So y and z is still is equals to 1, and x is greater than 1. So this sort of three-dimensional strain is called uniaxial extension. Okay. Now then, there could be another particular situation where axially symmetric extension can happen. So x becomes much greater than 1. Y is equals to z equals to less than 1. So that means there is strain in all direction. X is getting sufficiently stretched, okay, sufficiently stretched. Y and z both are getting equally squeezed. Y and z both are getting equally squeezed. Okay, hence this is less than 1. X is more than 1, this because this is stretched quite a lot. Now, in here itself, we can place plane strain where x will be greater than 1, y equals to 1, and z is less than 1. That means, we are squeezing from one direction, that is z, and it is getting stretched in the other direction, that is x. So squeezing from z, stretching from x, but y is remaining constant. There is no change in y. So this particular type of strain, by definition, is called plane strain type of deformation, as we have mentioned before as well. Now there is another type of deformation which we call axially symmetric flattening. So where x is much larger than y is much larger than y, z is less than 1. Okay. Sorry, x is larger than 1, y is larger than 1, z is less than 1. So that means as if we are pressing it from one side and allowing the material to flow in both the direction. So x can be equals to y, x might not be equals to y. Okay, so that means it is getting stretched in both x and y direction, but it might be equal, might not be equal, and this is what we call as axially symmetric flattening. Okay, now this is what we call flattening, and the axially symmetric extension, that is what you are seeing, like the cube is becoming like a stretched cylinder. This sort of strain is called constrictional strain. This is called a flattening strain, and this sort of strain is called constrictional strain. And we will see more example of flattening and constrictional strain in next couple of slides. And this is, of course, the most ideal one, that is the plane strain, where the deformation is only happening in one plane. Is this clear so far, guys? Can someone explain? Can someone tell me? Is this clear? Why there are only 10 students today? What's up, guys? Only 13 students? Okay, it's clear. Okay, let's proceed. So now let us dive into more details of the on the strain ellipsoid. So in 2D, the shape of the strain ellipsoid is described by one number, that is r. If you remember, r is nothing but the ratio between x and z. Okay, we did not need x, y, z there. We just kept x and y, if you remember. So if I just consider two dimension, only two directions would be there. So r is the ratio between x and z. Okay, only two distinct, because y is irrelevant. Now in 3D, the shape of the strain ellipsoid is described by two numbers. One we call as R12, that is the ratio between x and y, and the second one is R23, that is the ratio between y and z. Okay, so the ratio between these two parameters, R12 and R23, distinguishes the different shapes of the strain ellipsoid. So we are defining here a parameter which we call as k. K is nothing but a ratio between R12 minus 1 and R23 minus 1. Okay. Now the minimum value of R12 and R23 is 1. So the value of k would then range between 0 to infinity. Less than equals to, greater than equals to 0, less than equals to infinity. That is where my k value would essentially vary. If I change the value of the minimum value of R12 and R23 to 1. Okay. Now every ellipsoid can be reported as a point in the Flynn diagram. So based on these, like you remember, we plotted the different 2D strain in a XY plot, yeah, in a X by Y plot, and we defined that R value through a line which has a slope of 45 degree. Similar diagram can be produced for 3D, and such diagram is called Flynn diagram. Okay? And every strain can be reported as a point in that particular Flynn diagram, like we have done so for two-dimensional strain ellipses. Okay, so where R12 is plotted vertically against R23, and k value describes the slope of the line passing through the origin. We will see how it is in the next slide. Okay, so the diagonal of the plot R12 is equals to R23 defines plane strain condition. Okay, simply because x by y is equals to y by z, right? That's where R12 becomes is equals to R23. So that means there is no strain along y direction. Okay, there is no strain along y direction. So if there is no strain along y direction, what sort of strain pattern we are looking at? We are looking at a plane strain pattern, because we are squeezing from z, x is getting stretched, but y remains constant. Okay, so hence, if the value of value of k is equals to k is equals to 1, then we are looking for a plane strain condition. Okay. So let us see what happens then. Okay. So what we are plotting here, log of 1 plus epsilon 1 by log of 1 plus epsilon 2. The other way of looking at it is nothing but ln of x by y. Similarly, here we are plotting ln of 1 plus epsilon 2 by 1 plus epsilon 3. And the other way of looking at it is nothing but plotting ln of y by z. Now we said this is the line then that would essentially show me my plane strain. Okay, as you can see here, it is getting squeezed or stretched through the x or z direction, and it is getting flattened or constricted through the perpendicular direction. But the important part is y is remaining constant. Okay, y is remaining constant. This is what we call as plane strain. And for these two examples, you can see the corresponding strain ellipsoids. Okay. Now, if k is greater than 1, what that would result in something called constrictional strain. So k is greater than 1 and less than infinity, of course, right? Greater than 1, less than infinity. That means, it's like a it's like a stretching in one direction. Okay, flattening. Sorry, getting shorter in the other direction, in the other two direction, and the resultant ellipsoids looks like rod or pencil. The resultant ellipsoid looks like rod or pencil, and this type of this field is then called the constrictional field. The constrictional field is where k is more than 1 and less than infinity. Okay, now k is equals to 1, as we said, yeah, is called plane strain. If k is equals to infinity, that means x is much greater than y and z. So that means in one direction it is stretched proportionally higher than the squeeze in the other two direction, as if and in such a case, as if you can even cannot measure y and z direction. It is so much constricted. Yeah, it's a highly constricted ellipsoid, and that is where we put the axially symmetric stretching, and that is defined by the k is equals to infinity line. Okay, and then the other part of the coordinate is called the flattening coordinate, and here the strain ellipsoids look like a disk. So in constrictional coordinate, the strain ellipsoids look like call that as a rod or pencil. So strain ellipsoids look like rod or pencil. And in the flattening part, the strain ellipsoid looks like a disk. Okay, you can imagine how So if this is my strain ellipsoid, this I would say it's an constrictional ellipsoid. And if this is how my strain ellipsoid looks like, this is what we call a disk. So constrictional. This is constrictional. This is flattening. Constrictional means k is more than 1. And flattening means k is less than 1, more than 0. Okay, so so flattening, k is more than 0, less than 1, x is greater than y, greater than z. The ellipsoid have an oblate or a pancake shape, okay, or a disc shape, and plots below the diagonal line near the horizontal axis. Okay, axially symmetric flattening, that means it's just the opposite of axially symmetric constriction. Okay, axially symmetric stretching. It's just exactly the opposite. We can say k is never 0, though k is never infinity. I mean, there's very close to 0 or very close to infinity. Okay, so the flat ellipsoids plot along the horizontal axis. Okay, so by studying, so any three-dimensional strain that we will observe, we can essentially plot them somewhere in this particular Flynn diagram, and if it is a plane strain deformation, it will fit along the 45-degree line which passes through the origin, where the strain is restricted in only one plane, and for constrictional strain ellipsoids, the value of k is more than 1, and for flattening strain ellipsoid, the value of k is less than 1. Okay, so that's what the Flynn diagram tells us. Okay, now there could also be a volume change during the deformation. Okay, so a pure volume change or volumetric strain of an object is defined by delta V, of course, with V minus V0 by V0. So V is the final volume, V0 is the initial volume, and again V0 is the initial volume. Okay, so V0 and V are the volumes of the object before and after deformation, respectively. So the volume factor delta, or you can say delta V, is thus negative for volume decrease and positive for volume increase. I think should not be any problem in understanding this statement. So isotropic volume change happens when x is equals to y is equals to z is greater than 1, that is volume increase, or x is equals to y is equals to z less than 1, volume decrease. That means the volume is increasing or decreasing in equal amount from all directions, right? So the volume is either increasing or the volume is decreasing, but the increment or the decrease in volume is equal from all directions, and that is what we call as isotropic volume change. What is the other type of volume change deformation we can think of? That is the anisotropic volume change, where x and y and z are not equal to each other. Okay, and they are not equal to 1, and the two or all x, y, z's are different. Okay, they have different values, and that is what we call as anisotropic volume. And this is how different types of volume changes can be pictorially represented. So you can see the first one. So this is the blue colored box is the before deformation sphere, sorry, cube, and the first one is volume decrease, which is isotropic. X is equals to y is equals to z less than 1. Volume increase isotropic is x is equals to y is equals to z more than 1. Volume decrease anisotropic, x is equals to y is equals to 1, z is less than 1. Volume increase anisotropic, x is greater than 1, y is equals to 1, z is equals to 1. Y and z are equal to each other. And then volume decrease anisotropic, x is equals to 1, y is equals to z, but both of them are less than 1. So that is how we can describe different types of volume decrease related strain in structural geology. So far what we have been discussing, so there is an initial object, and that goes to some deformation, and it creates a final object or a final deformation. That is what we call as finite deformation, essentially, right? Now, finite deformation doesn't provide you a description of the path or the kinematics by which the initial shape actually got converted to something which looks like the present shape. Okay, so it doesn't provide you the kinematic path. So to understand the kinematic path, of course, we have to understand or we have to study progressive deformation, how deformation essentially progresses as some sort of external forces is applied on a particular object. Okay, so far we have considered as I said, the initial undeformed and the final deformed state of rocks. However, there could be many different ways to achieve the same deformed state of uh, form under state form and undeformed rock. Okay? So the typical tool is to use particle paths. Okay, as I have explained before as well in the introductory lecture of strain, that if I want to understand this infinitesimal deformation, if I want to understand this progressive deformation, the velocity vector or the velocity field is not going to be enough. Yeah, simply because the velocity field or the velocity vector essentially provides you a connection between the initial and the final, and it is completely independent of the process that happens in between. Okay, so that's why we need to more focus on the particle path, because we want to see the journey of a particular particle through the history of deformation. Okay, so we need to see the particle path, and that will provide us the flow pattern, how the material essentially flowed, whether they flowed similarly everywhere in the object or whether they flowed differently from one part of the object to the other. That is something we have to understand in case of progressive deformation, or in case of studying infinitesimal strain. Okay? So this is the example, like this is the initial state and this is the final state. You can see, so for the first example, in the first row, I have a progressive um, stretching going on in the same direction, and progressive um, squeeze is going on also in the z direction. Okay, so that is what is happening, and then this final shape is coming up. Okay, but if you see the second example, I see that the path taken by the second deformation is very different. Okay, so first there is some sort of constrictional ellipsoid being developed, and then the flattening strain ellipsoid is being developed, and final state is achieved after that. So if I just if I just forget about this part of the story, okay, this part of the story, if I look at the initial state here and the final state here, and the initial state here and the final state here, we will not be able to encounter any difference. But once we study the progressive deformation, we will be able to make out that, you know, both the deformation did not happen in the same manner. It actually happened it took, although the final product is the same, they both took very different ways. Okay. So if I try to understand the deformation, which is the pure shear type of deformation through the movement of the particle path, of course, you can see this is the initial step, and then slowly, with progressive deformation, how the shape is changing. Okay, and then we can now, if I have to just simply understand about the velocity, so this is my initial stage. Number one is my initial stage, and number three is my final stage. Now, if I just want to understand the velocity vector, what I am observing, so that this was my point P, which has come here, point P. So I can join them with a straight line, and this will be my velocity vector or my velocity field. Okay, so would be for this point and this point. Okay, I can simply join them in a straight line, and that will define my finite strain. But that is not how it happened. But I can see that these individual, say for example, this point P, had moved like this, to come to this place of P dashed. Okay, so there, as you can see, there is like a very different. So the particle path here is curved, of course, and is very different than the velocity field or the velocity vector. Okay, so when we are more interested in the finite strain, velocity vector is good enough. But in case if we want to study progressive deformation, velocity vector is not going to solve our purpose. We have to look at the particle path. Okay. Now, if I look at an example from simple shear, what I can observe, how the particle path is actually changing. So we can see that the particle path is essentially this particle. Yeah. So this particle comes here, and this particle comes here. Okay, and through a very complicated set of particle path history, which is given here. Okay, which is very different from the velocity vector, of course. Okay, So progressive deformation depends on the determination of the particle path. So you can see here the particle path of each individual point is actually drawn in case of simple shear example. So all these arrows essentially indicate how the particle moved with each stage of deformation. Okay, so this is where the particle path for both pure shear deformation and the simple shear deformation is kind of shown in a very simple way. Okay. Now, yesterday I asked you a question, if you remember, that I asked you, not yesterday, in the last class, I asked you a question that if I take particular line, okay, which maybe looks like this, okay, what would happen to this particular line with progressive pure shear? How this line will behave? Okay, whether it will, how the length of this particular line will change. Okay, and I asked you to find that one out. Has anyone got the answer? Has anyone tried to find an answer how it would change? Hmm? Anyone? Has anyone tried at home? How the length of the line will change through progressive deformation in case of both pure shear and simple shear? Has anyone tried? How about Prakriti? Have you tried, Prakriti? Saima, Suhail, uh, that's a little bit unfortunate. None of you have tried. Anand, have you tried? That's unfortunate. Okay, let me do it for you here. It's okay. So here you can see the progressive deformation is actually shown. Okay. Now let's draw that once more. So these are the particle paths, of course, and you understood how the particle path behaves. For the sake of simplicity, I'm just drawing one particle path. So that means the particle actually is moving like this through pure shear deformation. Okay. Now let us say I had a line OA at the beginning of the deformation. Okay. Now with deformation, what is happening? The line becomes OA dash. So what is happening? The length of the line is decreasing or increasing? Huh? Then it becomes OA double dash. Then it becomes OA triple dash. What is happening to the length of the line? It's decreasing, right? So with progressive deformation, initially the length of a line actually decreases till 45 degree. And what happens after that? I see that, you know, the length of the line starts to increase. So, and then there comes a point when, you know, it becomes, so OA is equals to OA. Yeah. There is a time when, you know, it comes back to its original length, and then it starts to get stretched again. Okay, so this is a typical thing that happens with progressive deformation of pure shear. I hope you understood that. And now, if I think of simple shear, okay, suppose this is a line I am considering. Okay, with simple shear, what happens? So OA, and then the point OA dashed. This also happens in simple shear. So there is an initial decrease in length. Okay, then the length becomes shortest here, and then again the length of that particular line starts to increase, and there is a point when it comes back to its original length. So uh, so OX becomes is equals to OA, and then there is the increase in length. Okay, so both for pure shear and both for simple shear, for pure shear and simple shear, what I observe, that the length initially increases of a material line, then it becomes, sorry, length initially decreases of a material line, and then it starts to increase. Okay. So how would the strain ellipsoid for pure shear would look like? Pure shear strain ellipsoid would look like something like this, where here is my compression and here is my stretching. But in case of simple shear, the strain ellipsoid looks something like this. So if this is the direction of shear, this is the direction of compression. This is compression. Now, if I observe this one, okay, what I should also be able to understand that suppose this is my direction of compression and this is the direction of stretching, and I can see, yeah, that at 45 degree, at 45 degree angle, till this, a material length of a line, the material length of a line is actually decreasing. Okay, so this is compression. This is this direction. The material length of a line is actually decreasing. And in this zone, and in this zone, the material length of a line is actually increasing. So in these two zones, material length of a line is actually increasing. And in these two zones, the material length of a line is actually decreasing. Okay? So this is what we call compression coordinate. And this part is called extensional coordinate. This part is called compressional coordinate and this part is called extensional coordinate. Simply because with progressive deformation, I can see that up to 45 degree angle with the direction of compression, there is a finite decrease in finite decrease in material length, and after that the material length actually increases. So that defines the field of compression, and that defines the other part, defines the field of extension. You can see it here. So this is pure shear, and the red dashed area is then the compression coordinate, and the rest is this white part is your, this part is your extensional coordinate. For simple shear, this is my compressional coordinate, and the rest is extension. This is compressional coordinate. Here is my extensional coordinate, and then of course I have the strain ellipsoid drawn here. Okay. Now, if I have a subsimple shear flow pattern, that means it's a mixture between so pure plus simple. Okay. So I have both pure shear and simple shear going on together. And depending on the proportion between pure shear and simple shear, I will be able to define my compressional and extensional coordinate. So I hope it is clear for you how compressional and extensional coordinates are defined. Now, the next topic that I'm going to talk about, that is what we call as vorticity. So vorticity describes how fast a particle rotates in a soft medium during the deformation. A related quantity is the kinematic vorticity number, which is 0 for pure shear and 1 for simple shear, and somewhere in between for sub-simple shear. So sub-simple shear is nothing but the mixture of pure and simple shear. Okay, so how fast a particle actually rotates. Okay, and you can see, you know that for pure shear the particle do not rotate simply because pure shear is a non-rotational type of strain. It's a non-rotational type of strain. Hence, the vorticity or the kinematic vorticity number is 0 for pure shear, and 1 in simple shear it is the maximum rotation that you can expect. Yeah, and hence the value is 1, and something in between, which is maybe in between the pure shear and simple shear, which we call as the sub-simple shear, and that is where we will observe the vorticity number in between 0 and 1. So I will, because we are going to discuss something else in the next class, so I don't want to continue right now. And I'll now answer any question that we might have around 3D strain. Please ask if you have any questions on 3D strain. Any point was not clear that I have just explained. Okay, if not, then I'll just stop the class here. I'll see you tomorrow.